effective field theory, which is locality. Basically, high energy effects are local, low energy not so much. And the basic, it's true for heavy particles. It's true for heavy parts of loop diagrams. So it's not just particles. But that's the first thing we did. We started by doing this, looking at integrating out a heavy particle in a vacuum polarization. And after renormalization, we got left over with something which is basically pi mu nu, which it was q mu q nu minus g mu nu q squared times alpha over 15 pi q squared over the mass of the heavy guy squared. Okay. And so here's something that has q squared in it. This is equivalent to a local Lagrangian. So this is an effective Lagrangian, which when you put the right factors in, it's alpha over 60 pi. There's a factor of 4 mh squared times f mu nu box f mu nu. Okay. So this vertex here is equivalent to just having this guy with a new Feynman rule where you just put a little x. This is side mu, side nu, q, flowing in, flowing out. That summarizes the effect of the loop. And if you take the matrix elements, you get just the Feynman rule that equals this. So minus I. M equals I times that guy. Okay. If we take other ones too, so other stuff, if we did this guy, we have 2 photons in, 2 photons out, where there's some heavy guy floating around there. This is the Euler-Heisenberg Lagrangian. And this Lagrangian is the effective Lagrangian of that is, well, it's alpha to the 4th I'm sorry, it's alpha squared over 90 mh to the 4th. And then it involves field strengths. It's f mu nu squared. And then there's 7 over 4 f mu nu dual squared, where f mu nu dual is epsilon mu nu alpha beta f alpha beta with a factor of 1/2. Okay. So when you're below the electron mass, for example, you add the usual f mu nu to this 1 over mh squared plus this guy, and you've got your low energy effective Lagrangian for QED. But of course, the opposite also happens if you had low energy particles. We saw this was the vacuum polarization for low energy particles we calculated earlier this semester, went like log q squared. You can't, that's not a local guy. You can't write a local Lagrangian for that. Okay. You guys back? Dartmouth, are you there?
Yeah.
Okay. I lost my ability to see you guys.
Okay.
Okay. Good. So that's the organizing principle. This is actually a good time to do this trick of integrating out a heavy field. Maybe you guys have seen this before. Let's just do it just to be sure that everybody's seen it. So integrating out a heavy field. Let's imagine that we have a Lagrangian that has a heavy particle in it. So I'm just going to be a scalar for me. Heavy squared, phi squared. Some coupling to light fields, F of psi, and then some light Lagrangian, L of psi. Okay, so these guys are the light ones. Phi is the heavy. So the full theory is defined by the path integral d phi, d psi, e to the I, 4x, L of phi plus L of phi psi, which is the second term, plus L of psi. And the idea is that you can do the path integral in this case over the heavy field, leave it just an integral for the light field. So we have d psi, e to the I, L of psi. Then we have integral d phi, the heavy field, e to the I, L of phi plus phi times this f of psi. So that's going to be, this is going to be some, let's all here call it z1 of psi. The effect of doing that. And so then we end up with something that just involves the light field. So we've integrated out the heavy field. So that's the phrase. Then here's how you do it. It's pretty simple. You complete the square. You take L of phi plus phi f of psi is minus a half phi box plus m squared. I've integrated it by parts there, of course. Phi plus phi f of psi. I'm going to complete the square by letting, so I'll let have box plus m squared acting on the Feynman propagator is a delta function. And then I'll define phi twiddle is phi plus integral d4y df of x minus y f of psi. Okay, so if we make that definition, then if I have minus a half phi twiddle box plus m squared phi twiddle, I have that combination. Well, it starts off with the same thing with phi. Then comes the cross terms where one of them is phi and one is this propagator. But box plus m squared acting on the propagator gives us back f. So I get, it's minus a half times 2 because there's two sides of it for the cross terms. And then there's a minus sign that I put into my propagator, so I make it a plus. Becomes phi f of psi. And then the last term has two of these guys. So it has propagator, box plus m squared propagator, box plus m squared kills one of them, and I get minus a half integral d4y f of psi at x df x minus y f of psi at y. And so that we have, just by doing this rewriting, let me take Z1 there. And I'm going to write the combination here, this combination in terms of this, subtracting off that guy. I've got a minus sign. I think my minus sign should not be there. Anyway, so here we have Z1 of psi is integral d phi e to the minus I d4x. Now there's phi twiddle box plus m squared phi twiddle. And then the second exponential is e to the minus a half integral d4x d4y f psi at x df x minus y f psi at y. At this stage, you just do you say that d phi equals d phi twiddle because we're integrating over all possible guys. This first piece just turns into a number, and we're left over with the. So you've probably seen this. I know I did the equivalent of this when I was doing perturbation theory. With instead of f of psi, we had a current. But this leaves the total z then as integral just d psi e to the I L of psi plus times this e to the minus I. Let me just abbreviate it as f df. So that's the integrating out part. Now the locality part is the following. We have df of x minus y is integral d4 q over 2 pi to the fourth e to the minus I q dot x minus y over q squared minus m heavy squared, where m heavy is taken to be big. So the trick here is you write this as integral d4q 2 pi to the fourth e to the minus I q dot x minus y. If this guy is heavy, there's a minus 1 over m heavy squared is the leading term. I'm Taylor expanding, minus q squared over m heavy to the fourth, plus blah, 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 blah. Which I can then pull outside the integral. So it's minus 1 over m heavy squared plus box over m heavy to the fourth plus dot, dot, dot. Acting on either the d4q over 2 pi to the fourth, either minus iq dot x minus y. Okay, so we've just taken the q squared piece and replaced it by box acting outside. This guy, of course, is a delta function. So in this limit, I've replaced this by delta functions, and then L turns into L of psi plus or minus, it's 1/2, that's plus 1/2 f of psi 1 over m squared f plus the next term would be minus 1 over 2m heavy to the fourth f of psi box f of psi plus dot, dot, dot. So this is, all these guys are now local. And that's the integrating out the heavy field. And just the usual caveat here is at low energy, massless particles are not able to be made local. If you had the same thing, df of x minus y, m equals 0, you can actually do the integral. So you just set m equals to 0 above. It turns into 1 over 16 pi squared, 1 over x minus y squared minus I epsilon. So it just depends on the distance, the invariant distance squared, but it's certainly not local. You could do the same, you could integrate it out, but you don't get anything local. Okay. So I went fast because I think you've seen basically that type of thing before, but we're going to use this in a few minutes anyhow. Okay, so it just saves me from doing it then. Any questions about it? That's not x squared, that's times, 1/2 times 2. Yes, okay, yes, no, I saw that too, and I was, it did look like an x. So the fact, there's the 1/2 from the fact that I had a half out in front, and then there was a times 2 because either the first phi twiddle or the second phi twiddle could have the term in, okay, 1/2 times 2. Good. Okay, so this leads to an organizing principle. Which is the energy expansion. And we've basically just seen it up there. we saw how the high energy effects could be expanded in terms of derivatives over m, the heavy mass squared. And so we basically are organizing powers of basically energy squared and momentum squared over m heavy squared. We treat this as a small parameter and organize things that way. It's not always a derivative expansion. Sometimes it's powers of fields, but one's removing the heavy field. Okay. So these are the easy organizing principles. The things I've done so far make it look like that I just use these things at tree level. Okay. So there's more to effective field theory than just these effective operators. So we've done effective operators, effective Lagrangians, or effective operators. Here's one. And so you see this all the time these days, especially at the LHC talks, because this is signs of new physics. But EFT is more than this. And that's, for general relativity, this is the interesting piece. The tree level stuff is pretty boring in general relativity. The loops are interesting. So you might think that you're just supposed to use these effective Lagrangians at tree level, since I've removed some portions of theory, and that's not true. I mean, here's an example in what we've already done. We took this diagram here and shrunk it to a point where there's the effective Lagrangian. Okay. Now, can you use that in a loop? Well, you know, you'd be hesitant to at the start because it looks non-renormalizable, but nevertheless you can do it. So let's take a look at a process here. Here's a process that I could use this in. This is subleading compared to normal stuff, but I could do that loop. Okay. That loop there actually turns out to be finite. It's power counting finite. And what it represents is, it represents this diagram, these two loop diagrams. There's two of them, two loop diagrams. But, you know, in these two loop diagrams, there are things like there's a cut right there. If you have a high enough energy to produce these particles, there's two photons, there's a cut, a discontinuity. An imaginary part comes in loops from there. That's a real physical process. You get that same physical process here in the effective Lagrangian. And in fact, in this particular case, there's no extra work done by doing since it's finite and both sets of diagrams are finite, you get the same answer using either the effective Lagrangian or doing the full two loop diagrams. And which would you rather do? You know, we've got this pretty simple effective Lagrangian. I can do a one loop on that one, but if you told me to go ahead and do those two loops, I'd be a little bit scared. It'd take me a long time. So the fact that Euler and Heisenberg did it for me once, I can just go and play with that one. This is little special example because everything's finite and I don't have any new divergences coming in. We'll see real cases where you have new divergences and all that stuff. But that brings me to the third organizing principle. This has to do with loops, renormalization, and what's called matching or measuring. So let me just do the philosophy here, and then we'll take an extended example where we do all these things. Okay, so here we go back. We know the divergences are from high energy. Okay, so I'm taking my effective Lagrangians and doing loops. Those divergences are not necessarily reliable. Okay, there could be many reasons why they're not reliable. If you've written an effective field theory that by integrating out some other particles, well, the other particles should contribute to the divergences also. So you're getting the wrong divergences. But even if you have the full theory, you're doing QED, we still think there's more physics happening before you get to infinity. So even the QED divergences aren't reliable. So in some sense, we don't really care about them, but we do care about that they're local. And so then if they're local, we can write out Lagrangians, and there's something there to renormalize. Okay, so one will go ahead and do such a step. Technically, you put the infinity inside the parameter. The second step here then is when you renormalize, you measure. And none of these parameters come given to you. So you get all your parameters in the end from experiment. There's two subcases here. Let me call them B1. B1 is a case where you have a known theory at high energies. So you've taken some theory, you had and integrated out a set of particles, had a light theory. You express then all the parameters in terms of fundamental parameters. So the ones of the full theory. So this guy is called matching. Basically, to do this, you take your full theory, you do some calculation, you take your effective theory, you do the same calculation, you match their parameters. I'm going to do this in the sigma model for you. But of course, that's not going to be available for us in a situation like gravity where we don't have a fundamental theory to match to. So if you have an unknown theory, you have to measure these things directly. Okay. So these then are no longer predictions of any theory at all. You just have to go out and measure them. The first matching, if you have an effect, a full theory, that's a little bit more predictive because the parameters all determined in terms of a small number. Here, there's more parameters that you just have to go out and measure, but that's okay. In the second one, well, I mean, an example, well, when I'm going to do the linear sigma model, and then I'll tell you that it's like chiral perturbation theory in QCD after I finish it. The linear sigma model itself is one where you can match. The QCD is one where we don't know how to do the calculation, so you go out and you measure. It'll be the same set of parameters, but you have to measure them because you can't calculate. Okay, it's actually not an unknown theory, and in principle you could match them. In practice, that's only done these days on lattice calculations. These lattice calculations can match onto it, but until you do that, you just go out and you measure them in one process and then use them in some other process. Okay. And then the C is where the interest comes. You can separate then the high energy parts, because they're local again, from the non-local pieces that live at low energies, local, and predictions live there. So basically, after you've gone through and matched and measured, and you've got a set of parameters, then the effective field theory gives you some predictions that are not that. And that's where you get predictions. Okay, so that's what I hope to convey. This part here is the part that we're going to do for general relativity. We'll take those divergences, we'll renormalize them. We'll tell you how you would measure them in principle, and then we'll separate out the non-local stuff that's a prediction. Okay, so that's the goal. My extended example is the linear sigma model. Actually, anyone want to ask a question there? This is a break point. Okay. All right. Linear sigma model. This is a good model for us because you can construct the effective field theory by hand. So you can see the approximations made. But it's even better for this particular course because it's the effective field theory closest to general relativity in style. Okay, so basically everything that we say here, once you see how it works, you'll be able to see how general relativity works as an effective field theory. Okay. So let's go. Linear sigma model is basically the Higgs sector of the standard model. Here's the Lagrangian. The Lagrangian is 1/2 d mu sigma squared plus 1/2 d mu pi. So it involves a set of fields sigma and 3 pion fields, written in an invariant way, so those are squared. The potential is plus mu squared over 2 sigma squared plus pi squared. And then minus lambda over 4 sigma squared plus pi squared squared. So it's invariant that way. And then the usual sigma model also has couplings. It's a has a massless fermion plus then psi bar with some coupling, sigma plus I, tau dot pi, gamma 5, psi. Okay, I'm going to just carry the fermions around for just a little bit, but just because it actually helps us with the symmetry of the theory. But the tau is the Pauli matrices. So this is an isospin invariant interaction. And psi is a two-component. Psi is, well, in the original sigma model, it's the proton and neutron. But it's basically a doublet. It doesn't matter what you name it. Okay, so that's the full theory. The effective field theory that comes out of this is going to have f squared over 4 trace d mu u dagger. I've shown you this guy before. This is one of my examples for the heat kernel, where u is exponent I tau dot pi over f, and f in this case is the square root of mu squared over lambda. Okay. So part of our task is to get from the first one to the second one. That's part of our task. This is drop the fermions. I've taken the fermions out in writing this. So actually, it's even true even with the fermions. And there'll be corrections after this too, because we're going to do an energy expansion. Okay, so we're set. Sigma is going to be the heavy field, yes. So, right. So this is going to be one that's going to have spontaneous symmetry breaking in it. So we've got a symmetry. The standard analysis is then we find the ground state. We find the sigma is heavy, the pi's are massless, and the fermion becomes heavy. So the fermion becomes heavy too. Right now it has no mass to it, so it's a massless fermion, but sigma is going to pick up a vacuum expectation value. And so therefore this G sigma is going to be the mass of the nucleon. Okay. So this is the Higgs sector. In the Higgs sector, you, instead of sigma and pi, you write phi is phi 0 plus I phi 1, phi 2 plus I phi 3. But the phi 0 is the sigma, and phi 1, phi 2, phi 3 are the pi's. Okay, so there's a one-to-one mapping. The way to this is a one-to-one mapping between phi 0 and this is the Higgs, and phi 1, phi 2, phi 3 are the unphysical Goldstone bosons that get eaten up to form a massive W in Z in the standard model. Okay, so this is our goal, and let's start the pathway there. this first thing I want to do is rewrite the Lagrangian. I'm gonna, geez, sorry. So there's the Lagrangian. I want to define the object that sits right there as capital sigma. Sigma is sigma plus I tau dot pi. Okay, then if I do that, then sigma dagger sigma, well, is sigma squared. The cross terms cancel. It's then plus tau dot pi squared. Tau dot pi is just pi squared. But just to make this obvious, I'm going to put a trace, a 1/2 trace. So 1/2 trace. Then the trace of tau I, tau j is delta ij, 2 delta ij. So this is then sigma squared plus pi squared. I actually didn't have to put the trace there, but I need it for later stuff. Okay, so without any approximations, just by using this notation, I get the following. I get this first piece here has 2 derivatives. I can write that as is 1/2 trace. That's actually 1/4 trace of d mu sigma dagger d mu sigma. So these are, the sigma is a 2x2 matrix. So I take 1/2 d mu sigma dagger d mu sigma. That gives me the sigma squared plus pi squared pieces. Then I get plus mu squared over 4 trace sigma dagger sigma minus lambda over 16 trace sigma dagger sigma squared. And then just the later on, the fermion piece is plus, it's the following. It's G psi bar left sigma psi right plus psi bar right sigma psi left, where I've used the following. I've used psi left is 1/2 1 plus gamma 5 psi, and psi right is the one with the minus psi. Okay, so I actually okay, let's save my note. Let's get back here. Yeah, this is a new one. There we go. There it is. Okay, and anyone have questions about that rewriting? It's really, there's no approximation made here. That's just what it's just identical. I've just used this matrix notation to replace the d mu sigmas and d mu in various ways. And then this guy, I actually did relatively quickly, but to get the gamma 5 there and the sigma, I don't know. It's you can. And one of these is daggered. One of these is daggered, yes. The right one, this one is daggered. Thank you. one purpose of going through this little step is it's an intermediate step to later on, but it also shows you the symmetry of this. If we take psi left goes to some left rotation, psi left, so this is some SU2 matrix. Psi right goes to some right SU2 matrix. And we take sigma goes to left sigma right dagger. Then all these things are invariant. Okay, so the couplings, the Fermi couplings, that's why I sort of kept them along. It makes this obvious, but I could have just done it right up here. The psi dagger, or sigma dagger sigma traced is invariant under that transformation property. Okay, you can sort of see it if I do trace of sigma dagger sigma, it goes to trace, well, I get L sigma R dagger, and over here I get L dagger sigma dagger R dagger, R, not undaggered now. These guys cancel, and these are the properties of trace. Those guys cancel, so we're invariant. Okay, so we're going to want to have our effective Lagrangian have this symmetry also after we get done with it. It's actually, you can see it coming out here. There's, in the end, I'm going to have this, and I'm just going to impose a symmetry on this, which is U goes to L, U, R dagger, going to be the symmetry. We got the same symmetry again. All right. Now, the predictions of the theory, well, we do go through spontaneous symmetry breaking. There's a minimum in that potential that breaks the symmetry. The symmetry is, okay, let's just say it up here. Symmetry is SU2 left cross SU2 right. SU2 right. There's a minimum of that potential, the way I've defined it with the minus sign in the potential, that we can place in any direction we want, but we'll place it in the sigma direction. At the minimum, the sigma field is the square root of mu squared over lambda. The pi field at that place is 0. That's my choice. And then for my later work, I actually have to write out the Lagrangian. So basically, you would then say sigma is this guy here, which is V or F, depending on how I want to do it. V in the standard model plus sigma twiddle. And the Lagrangian then looks, so I just, excuse me, I have to write it out. It's 1/2 sigma d mu sigma twiddle minus 2 mu squared sigma twiddle squared. Then there's a 1/2 d mu pi with no mass term. There's a coupling minus lambda v sigma twiddle squared plus pi squared. So this is a triple coupling. There's the lambda phi to the 4th. sigma squared plus pi squared squared. The nucleon picks up a mass, so it's psi bar I d slash minus G V psi. And then there's the nucleon couplings left over, G twiddle, G, no twiddle yet. Psi bar sigma twiddle plus I tau dot pi psi. Okay, so the sigma guy gets a mass, the nucleon gets a mass, the couplings here. And the only thing new is these new couplings. Those came from redefining the potential in terms of sigma and pi, okay? Any questions about those guys? Those actually play a little role in what we're doing. Okay. But at this stage, it's somewhat standard. Okay. So now, to get the effective field theory, let's see. I'm going to take this Lagrangian and go straight to the effective field theory and then do some calculations. So okay, so the trick for getting the effective field theory is to take this original field, these sigmas, and put it in a new form. So remember, sigma was sigma plus I tau dot pi. And I'm going to write, so that's a 2 by 2 matrix. I'm going to write that as V plus S times U, where U is this exponential, e to the exp. I want plus I tau dot pi over V. Okay. Okay, so if you look at this, I'm sorry, was there a question? Is there a question?
No.
No, okay. All right. S is a new field. Okay, so basically what I'm doing, let's see, this is pi prime. I'm defining a new set of fields. Instead of sigma and pi, I've got S and pi prime. And V is the expectation value that we had before. And remember that we define this as V plus sigma twiddle plus I tau dot pi. And on the other side here, I would have, well, I have V plus S is how it starts out. If I expand the exponential, I get a 1 is the V plus S, and then the tau dot pi prime, the first order piece, there's a V, 1 over V cancels the V, I get then I tau dot pi prime, and then I get higher order terms. So to first order, so sigma twiddle is S plus higher order terms, and pi is pi prime plus higher order terms. So I've just gotten a renaming of the fields. Okay. So again, without any approximation, I'm going to rewrite the Lagrangian. Okay, so the Lagrangian here is a half d mu s minus 2 mu squared. I'm sorry, d mu s was squared, of course, s squared, 2 mu squared. And then the kinetic energy pieces that were d mu pi's, well, d mu sigma I had. Okay, let's actually just go back and think about that. I had, without any approximation, I had d mu sigma dagger, d mu sigma. So there's a case where the derivatives act on the s field only, and then the u dagger u's drop out. Oh, sorry. So I had d mu s squared from that. The things where it acts on the u's, I end up with v plus s over 4 squared d mu trace d mu u dagger. Okay, and then I end up with minus lambda v s cubed minus lambda over 4 s to the 4th. And then let me not bother writing out the fermion side. The fermion side is not interesting for us now. Okay. So again, this is really no approximation. I haven't dropped anything when I've done this. I'll write that. I've just taken the sigmas that I wrote up above there and wrote it in this way. Now, one of the nice things that happened is when I had sigma dagger sigma, that the u's dropped out. So there's no pi's in the potential. Okay? In the potential. The only place the pi's live are right here in the kinetic energy pieces. So what have I done? Well, the particles have the same masses. This is a massive particle, so S has the same mass as the sigma. The pi primes are massless still. There's no mass term for the pi primes. What I've got is I've rewritten this thing in a it looks very funny. I mean, there's no difference between these two Lagrangians. Up here, I've got polynomial couplings in the pi's and the sigmas. Down here, the next step, sorry. Next step, I have polynomials in the s's, but only derivative interactions with the pions. Okay. So the way we would imagine dealing with this is to integrate out the sigma, or the s in this case. Okay, well, some of these guys are going to end up being equivalent of loops. So the s cubed, the s to the 4th ends up being loop-like. But the first approximation is you just drop s altogether. It's heavy. Appelquist and Carozone tell us that heavy particles have effects that are power suppressed. So we invoke Appelquist and Carozone. By the way, I think it's I looked up Carazone, and I think it's Carazone. So there's two Z's. And this, if I do that, I just say I'm not interested in the S at all. It's a heavy particle. I don't want to deal with it. I end up with my effective Lagrangian. This gives me L effective Lagrangian is V squared over 4 trace d mu u dagger. Okay, so there we've constructed the first term in the effective Lagrangian, and part of the work the more interesting part of the work is getting the rest. Okay, I've dropped the fermions because they're heavy too. Okay, so they're heavy, and in practice I'm going to drop them from now on. Just I will calculate the effects of this heavy particle, the S or the sigma. I'll show you those at tree level and loop level as we go, but I'm not going to do the fermions at all. Okay. So, but here's the first test. Let's show you that this works by calculating something with the effective theory and the full theory. Okay. So here's how it goes. What I'm going to do is I'm going to calculate my example is pi, that's pi plus pi 0 goes to pi plus pi 0. Okay. Let's do the full theory first. Okay, so in the full theory, here we've got it up here. There's two places you can see I can make the transition here. There's a pi dot pi vertex that comes from there, pi dot pi squared. So this guy gives me, there's going to be a Feynman rule that looks like that from it, and it will make my transition. And also up here, there's a pi squared there with a sigma. So pi squared sigma, this guy gives a vertex that looks like pi sigma. I'm doing this calculation at tree level, so I'm going to write the two diagrams. Here's the one diagram, and the second diagram is this guy. Pi plus, pi 0, pi 0, pi plus, pi 0, pi 0. Okay. Well, so the Lagrangian that I'm working from here then is I need lambda over 4 pi squared, and then this piece was lambda v sigma twiddle pi squared. Those are the terms that make this happen. I have I times the matrix element. Well, the first piece gives me minus 2i lambda. There's factors of 2 from, let me not do factors of 2. The second piece gives me, there's a factor of 2, so it's minus 2i lambda v. There's the coupling, squared, 1 at each vertex, and then there's an I over q squared minus m sigma twiddle squared. Okay. This is, so let me factor out minus 2i lambda. I get 1 plus, what's left over here is 2 lambda v squared and q squared minus m sigma squared. M sigma squared was 2 mu squared, which if you go back and plug in what v is 2 lambda v squared. Okay. Well, this, you see, there's a funny cancellation going on here. I've got q squared minus 2 lambda v squared and 2 lambda v squared upstairs. If I set q squared equal to 0, those that's a minus 1. 1 minus 1 cancels. I get my first term is then I q squared over v squared. Okay. I have to Taylor expand that. I get q squared over v squared. All right. So there's the full theory calculation. Now, the effective field theory calculation. So this is now with the effective theory. Or even in the, I can even go back and up here, even including S. My first term is just the one I wrote down here. You can see actually there is going to be an S exchange term here too. And it's actually interesting. Let's do it. If we did, this guy is going to come out of L effective. And then we could have done this with S exchange. Okay. This guy, however, has trace d mu u dagger at the top. That can give you a matrix element. It's 2 derivatives. It has trace d mu u dagger down at the bottom. That has 2 derivatives in it. So this guy, even if we were just starting calculating from this other form up here, so even before I form the effective Lagrangian, just calculating from this form here, I would have a piece that is the effective Lagrangian piece, and then there's a S exchange piece coming out of the Feynman rules. But that S exchange piece now all of a sudden is of order e to the 4th. This is of order q to the 4th over m s squared. And that q to the 4th is a power beyond what I've kept here. So I just need to take the effective theory. There's the effective theory. I have to then write out the interaction piece here. I Taylor expand that, and it looks like the following. It looks like 1 over 2 v squared. It's the piece I want is it's phi 0 d mu phi 0 plus phi plus d mu phi minus plus phi minus d mu phi plus, and then I square that. That's, I've had to do a little Taylor expanding to get to there. But then I calculate this vertex here, and I get IM. Well, I get a derivative at the upper part, a derivative on the pi zeros, and a derivative on the pi pluses and pi minuses. They both give me a factor of q. I get I q squared over v squared. Just like in agreement with the calculation before. I'm sorry, those are pi's. Sorry, those are pi. They should be pi primes. I'm sorry. They're pi primes. And actually, because that would only give a loop. Okay, so the question is why not pi squared sigma squared? If I had that vertex there, so pi sigma, and I want to do scattering, I have to do something. I could do that diagram, or I could do, so that's a loop diagram there. Okay, or I could do that diagram where I'm just doing tree at this stage. That's right. Right. So I'm starting off just doing the simplest thing, and then we come back and we do loops. Okay. All right. So actually, let's just make a comment or two and stop here. Basically, what I've done is you can see that either of these two theories give me the same answer. I could rewrite the Lagrangian this way, get that answer. I could rewrite, keep the Lagrangian in this original form, get the same answer. And I also get the same answer leading order by just dropping the S altogether and using the effective Lagrangian. Okay, so there's two things going on here. One is I got the same answer using these two forms here, even though they look like they're very wildly related. One is a polynomial theory, the other is an exponential theory. That's an example of what's called Haag's theorem. Basically, you're allowed to do any renaming you want. Names don't matter. You can do any renaming you want. The only condition on Haag's theorem is you have to have your fields start off the same way. So sigma turtle, it was S, pi prime was pi, plus dot dot dot. So the first order they have to match, and that's just to keep the kinetic energies the same. So basically, if you have the same kinetic energies and masses, then names don't matter. All right, so that's the place to stop. Well, I'll come back and I'll first just do the tree level matching to the full theory to the effective theory. Then a little bit more work goes into the loop level matching. Okay, but then we get to see the loop level matching is the interesting one. The tree level one's boring. Okay. All right, so after spring break comes up next week. We'll see you after spring break.
All right, thanks.
Yep. Bye-bye.